In this video I'm going to discuss how to build this simple electronic game. It's based on a game called Kill the Bit, and I'll go through the history of the game, I'll demonstrate the game, and I'll go through the circuit diagram, and I'll talk about how to actually put the game together. This is the front cover of a magazine from January 1975. The magazine was called Popular Electronics, and it talks about the first microcomputer kit. So this was before we had home computers, and it was just when the first kits for microcomputers were coming into homes for hobbyist electronics users. And it shows the actual Altair 8800 and how basic it was. It just had LEDs on the front panel and some switches. And people originally programmed this using the switches and the LEDs on the front panel, and so you couldn't really do much with it. And someone came up with this little game which lit up some LEDs and rotated an LED on the LED display, and you had to extinguish that by switching one of the switches. So I made this circuit, which is a simplified version of the game, and it runs for CoinCell. And when you turn it on, it just has the one LED going across there. And when it gets to this end LED, you've got to try and press it to extinguish the LED, and you've got a reset button which starts off again. And if you hit when you're not on the LED, it'll light more LEDs, and you can just press the reset button to go back to the single LED again. But I've put a variable resistor down the bottom here so that I can change the speed of the game, so it makes it a bit quicker. It gets harder the quicker it is, the harder it gets, of course. And if it gets too complicated, just hit reset and then start again. I've made it so that the fastest the game goes, it's pretty much impossible to do, because it not only relies on you hitting the LED when it's there, but only hitting it for the single period that the LED's on for. Otherwise you light up more LEDs, and so at the fastest speed it's just pretty impossible to do. So I'll discuss the circuit, and then I'll go over the circuit diagram. So if I just switch it off. So I try to make it as simple as I can, and it just runs off of a shift register here, which is 74HC595. And you need the HC one if you want to run off of 3 volts, because it is a CMOS version which can run down to 2 point something volt, 2.7 volts or something like that. And I can also drive the LEDs directly because it's just running off a coin cell battery. I don't need resistors in between the shift register and the LEDs. I can just run it directly from the voltage of the battery. If you want to run it off of 5 volts, you can run it off an HC or any of the other types of this version of shift register, which run on 5 volts. But you also need to put 220 ohm resistors in there. But it keeps it nice and simple, the fact that it just runs off of a coin cell battery. And like I say, there's a variable resistor to change the speed of the game. This button flips the LED, so turns one off if it's on, or on if it's off, when at this very end. And then this is just a reset button which goes back to a single LED animating across the display. So I'll go through the description of the circuit and how it works. Soon after this video goes live, I'll put this circuit diagram and the Gerber files for making the PCB on my GitHub page. I'll put a link to my GitHub page in the description. So I've got a 3 volt battery here and a switch to switch on the power. But I have a 1 microfarad capacitor here just to smooth out any noise that occurs when you close this switch, so that it doesn't affect the circuit. And I've got a 10 nanofarad capacitor there, which goes for decoupling across this integrated circuit here. And the next part of the circuit is the oscillator, which decides how fast the game is going. So I've got a variable resistor up here which controls the speed of the oscillator, and this is just a standard flip-flop circuit which you'll see all over the place. Very handy circuit to know. And it just charges up one of the capacitors and switches transistors on or off, and then charges up the other capacitor and switches the transistors in the opposite direction. So at this point here you get the clock going in one high, say this is high and this point is low, and then when they switch, this point will become low and this point will become high, and it will just oscillate at the speed that you set it to. So I use those 2 points to do 2 different things: one to shift bits into my shift register, and one to latch the bits onto the LEDs. And this next part here is the reset circuit. So I've got a reset button, but also when you power up the circuit, it does the same thing as pressing the reset button. And so it's got a capacitor there, quite high value, and a quite high value resistor. And the capacitor charges up from switching on the circuit, and it just clears the shift register, so there's no bit set in the shift register when you power on, or if you press the reset button, it'll short out the capacitor, and it will act like then the circuit's being switched on again when you release the reset button, and just clear the shift register. But clearing the shift register will just clear all of the LEDs, and you won't have any of them lit. So you need to actually light one of the LEDs in order to start the game. So I have the signal coming up here, and it's a signal is saying the reset button's been set, so we need to set one of the bits of the LEDs. So that'll happen whenever, like I say, when it's powered on, or if you hit the reset button, this will then go low. And this diode here says you can pull current through here. So if it allow this side being low to affect this circuit here, but if this side is high, then it won't affect that circuit. So it's only when this side goes low and when it's in reset that it will actually set this. And this circuit looks a bit like this circuit down here. It's got 2 transistors, but rather than capacitors, it has a couple of resistors there. That's because this is kind of like a flip-flop latch. And so on resetting, it will actually set this bit high, and it allow current to go out this way, so it allow it to set high. So this is, I've labeled this reset bit, and this goes into the shift register as setting the bit. So at this point in the reset cycle, we're actually putting the 1 in there. So when it clocks, so this is still oscillating, nothing's affecting the oscillation, so this will still oscillate. It'll shift that bit in. But you see on this first output, I'm taking the signal out there, and I'm calling it reset bit confirm. So I'm confirming that we've got 1 bit set on the shift register, and because that's high, it allows it to go into here, and it allows us to set this high. So the reset set it low, but now we're latching it high again. Because that's high, this bit is low, but because current is only allowed to flow out, not in, that won't affect the circuit in any way. It only affects the circuit when you want to set the bit. So that's been now reset. So this circuit is now out, not affecting the rest of the circuit in any way. And we've got 1 bit set, and this is still oscillating. And so that bit now will rotate around here. And we don't have to worry about this reset bit in here because we're not pressing the reset or anything. So that won't affect the circuit at all. And we've got a bit rotating around our shift register, going from shifting the bits on one cycle of the clock and latching the bits to the output on the other cycle of the clock. So that starts the game up and it's running. So now the only bit left of the circuit is actually when someone presses a button. So when the bits come down to when the bit comes down to the bottom of the LEDs, we actually want it to go back up to the top one because it's going to keep rotating around in a circular fashion without anyone pressing the button, and that's what this QH overflow on the shift register is. So take the carry bit out of there and it goes into this circuit here. So these 4 diodes make up an exclusive OR gate, and then this NPN transistor inverts the signal from the exclusive OR gate. And so if I talk in terms of LEDs coming around here and getting down to this point, if it's extinguished it'll be a 0, if it's lit it'll be a 1. And this is the user button. By default it's pulled up to 3.3 volts, so by default it's high, and if someone's pressing the button it'll be a 0. So first of all, no one's pressing the button, there's no LED here, so 0 and a 1, exclusive OR is a 1, which gets inverted to 0, so the extinguished LED gets wrapped around. But if there is an LED here, so 1 and a 1, which exclusive OR is 0, so that gets inverted to a 1, and the LED gets wrapped around and continues to rotate around the shift register. So now if someone's pressing the button, so this point is now 0 here, so no LED coming around, which is 0, and 0 here, exclusive OR is a 0, so then the inverter makes the LED lit. So whereas it wasn't lit, now it is lit. So by someone pressing the button, it inverts the LED, and you get a new LED getting rotated around the shift register. But if there is a LED coming around, and someone's pressing the button, so that's 1 and a 0, which is a 1, gets inverted to 0, so that's the LED is now extinguished and it gets wrapped around. So by the user pressing the button, it inverts the LED, but if they're not pressing the button, the LEDs just keep continuing around the circuit as they were previously.